to CHeM in 3, the series where we spend no more than 333 seconds to consider 3 important points for the IB chemistry exam. In this episode of CHeM in 3, we look at orbital hybridization. Carbon has 6 valence electrons arranged in accordance with this electron configuration: 1s2, 2s2, 2p2. This can also be written as helium core, 2s2, 2px1, 2py1, and 2pz0. Here we consider the 3 lobes of the p orbital system: the x, the y, and the z. When a carbon atom undergoes sp3 orbital hybridization, one of the 2s electrons is promoted to fill the 2pz orbital, and then all of these 4 orbitals coalesce, join, or hybridize to form equivalent hybrid orbitals. These 4 equivalent hybrid orbitals then have 25% s character and 75% p character. A hybrid is the product of 3 p's and 1 s. Once these 4 equivalent orbitals are created, then it allows for a molecule like CH4, methane, to form 4 equivalent bonds to 4 hydrogen atoms. And each of these bonds exists as its own electron domain. So CH4 has 4 electron domains, and these 4 electron domains give rise to a tetrahedral structure. So we can say then that 4 equivalent hybrid orbitals from any atom can give rise to 4 electron domains, and then a tetrahedral electron domain geometry. And this can then be used as a quick way of saying that the orbital hybridization of this atom would be sp3, and this gives rise to a tetrahedral structure. In the case of ethene, the s joins with only 2 of the p orbital lobes, forming what is known as an sp2 set of hybrid orbitals, leaving this free p orbital to carry out its own bonding. These sp2 hybrid orbitals would then have 33% s character and 66% p character. But with these 3 equivalent orbitals being formed, it means that a molecule like C2H4 would have 3 identical bonds from the 3 electron domains created as a result of the sp2 hybrids. But also a part of this electron domain between the carbon atoms is another type of bonding, one where the free p orbital overlaps with the free p orbital of this carbon to form what is referred to as a pi bond, whereas the 3 hybrid orbitals form sigma bonds. So in the case of ethene, we do have 3 electron domains, but 4 bonds. 3 of the bonds are sigma bonds coming from the sp2 hybrid orbitals. The 4th bond that belongs to this 3rd electron domain comes from the overlap of the free p orbitals. This is known as a pi bond. One here with 2 bonds, but 1 electron domain, and these 2 electron domains. 3 bonds resulting from the sp2 hybrid orbitals, and the second part of the double bond resulting from the overlap of the free p orbitals, pi bond. When we have 3 electron domains, like in the carbons of C2H4, then we have sp2 hybridization, and the shape is trigonal planar. All 3 bonds are in the same plane, forming this triangular shape, trigonal planar. And finally, we look at C2H2, ethyne. The 2s orbital hybridizes with just one of the 2p orbitals, forming two equivalent orbitals. The hybrids would have 50% S character, 50% P character, and these two P orbitals would be left free to form bonds of their own, pi bonds, whereas these hybrids would form sigma bonds. This means that a carbon here in C2H2 would form a single bond with this carbon and a single bond with this hydrogen, and that would take care of the two hybrid orbitals, the sigma bonds. But then these two free p orbitals would overlap with the free orbitals here and here, giving rise to two pi bonds. Even though you have 3 bonds here and 1 bond here, you only have 2 electron domains. And 2 electron domains goes with sp hybridization. And the shape? A straight line, linear. sp, 2 electron domains, linear. sp2, 3 electron domains, trigonal planar. And sp3, methane tetrahedral. So now it's time to see if you can identify examples of sp, sp2, and sp3 hybrid orbitals.